So got that. Next on the agenda, let's look at this review quiz that you guys are working on right here. So you guys have had this for a while and it's due next Friday. So after the SAT, okay, but give you guys some pointers here. So the first question, there's a block sliding up an incline. Notice I gave you guys a velocity vector, okay? And there is friction. And I want you guys to draw the free body diagram. And I give you guys a hint, there's 3 forces. Now, this free body diagram is going to look different than if the block was at rest. Okay? How about this? If the block is sliding up to the right, which it is because I gave you guys a velocity vector, right? For free body diagrams, what's the only kind of vector you care about for free body diagrams? Force vectors. And if something is moving in a certain direction, does it have to have a force in that direction? How about this? What if you have a car braking to a stop? Car brakes to a stop. Road, car. Maybe it's like moving to the right. Right? What would the free body diagram look like for that car? Just get a weight and a normal force and like a friction force that slows down, right? Is that it? I think that does it, right? Huh, okay. Number 2, ooh, there's a classic double elevator outlet. I've got some time at the end of class, I might do some of those with you guys, but we've done a lot of those. You guys did a whole lab on those. Right? Oh, and the question is, what is the tension in the string? Actually, here's what I will mention about this. Right? The way I always lead you guys through these problems is I had you guys solve for acceleration first, like the downward acceleration of the heavy one, for example, right? Or the upward acceleration of the light one. And then after that, what I have you guys do is hone in on one of those blocks. So either that one or that one, and do an individual free body diagram, and then you can solve for the tension that way. Okay. That's the way I always lead you through those. But there are some textbooks that do it opposite. Sometimes they'll have you solve for tension first and then acceleration after. Now, I think that's confusing, but there's a way to do that. So I don't know. You pick your favorite way. You guys can do outputs. Number 3, I'm going to leave to you guys. Now, number 4, I referred back to number 1. So number 4 and number 1 really go together. And I gave you guys some numbers. I gave you the mass of the block, I gave you the angle of incline, and I gave you a specific coefficient of kinetic friction. And I asked you guys, can you solve for the acceleration of the block? So you do have to get number 1 correct to get number 4. Right? Like if you don't draw the correct free body diagram, then you're not going to get number 4 right. So number 4 says, what is the acceleration? Acceleration. Shouldn't the last step be something to do with Newton's second law of motion, right? Net force divided by mass? Right, and I think you guys can get that if you guys know how to navigate that type of question. Sorry, just in case you're wondering, like, why didn't I make that question number 2? So, kind of a design thing. I want to leave you guys some space here so you could draw a free body diagram, and there would be like no eek in the way of drawing a free body diagram right on that block. Number 5, I'll leave to you guys. Number 6. Right, it's going to explain the context of this question. So we've got an astronaut, has a mass of 60 kilograms, or whatever number is on your paper. Okay. So on Earth, maybe he weighs 600 newtons, makes about sense. And on the moon has about 1/6 of Earth gravity. Maybe I should have just said 100 newtons, but here I said 96. So, okay, so something like that. Okay. But the actual question is, what is the gravity force? With what gravity force does Earth pull on the astronaut when the astronaut is on the moon? So the astronauts bounce around on the moon. Do you guys think that there's a tiny, tiny gravity force from Earth a long way away? Right? And if you look at all the answer choices, they're each less than a Newton. So whatever the correct answer choice is, right, it's just going to be a small fraction of a Newton. Right? But to answer this question, you would have to know how far away Earth is. And that's where I told you how far away the moon is from the Earth in terms of the radial size of the Earth. Right? Now, I gave you guys 4 numbers here. I mean, obviously 4 boxes, you don't need all the numbers. You might only need some of the, I don't know, maybe 2 or 3 boxes. But if you know the distance of the moon in terms of the radial size of the Earth, isn't that maybe something to do with the inverse square law? Maybe something like that. Oh, number 7. Oh, okay. Just going to the picture, I see like a ball on a string, maybe swinging around a circle. Okay. Now, whenever I see a picture like this, the first question I'm asking myself is this a vertical circle or a horizontal circle? Because the mechanics of those would be different, wouldn't they? Okay. Do you guys see this right here? It says aerial view. That means this is a what kind of circle? Horizontal. See, we're up in a blimp looking straight down, and we're seeing somebody swing a horizontal circle around, right? Maybe there's a ball on a string. Okay. Does that mean that there's probably a pretty good likelihood that the speed is constant going all the way around? Yeah, right. I mean, if it was vertical, no way. But horizontal, yeah, probably so. Right. And the question is, what is the tension in the string? That's the actual question. What is the tension? But notice there's actually a pair of answers because there's a couple of interpretations you could do on this. The follow-up says, what is the actual tension once you consider the weight of the ball? One of the things I wanted you guys to see is that no matter what the correct answer is, that when you include the weight of the ball, it doesn't actually change the answer a whole lot. For example, what if the answer was A? I don't know what the answer is, but maybe it's option A. 5.36 newtons compared to 5.46 newtons. Okay, that's not really a whole lot different. Right? Now, why would there be a difference depending on how you go about solve this? What am I talking about? Why would you get possibly 2 different answers depending on what you consider? Okay. So let's get a side view of this. Let's have like a central axis. Maybe like here's the orbit of this ball going around that central axis. Okay. And then here's a string that connects to this ball. Something like that. Okay. Guess that? Do you guys see sort of like a cone type shape? You guys see like a cone shape, right? And notice that string does not pull straight horizontal. What physical factor what physical variable could you change to make it closer to a horizontal circle? What if you swing it faster, faster, faster? Wouldn't that like flatten out this cone, make it closer to a horizontal circle? It would. Can you ever have a perfect horizontal circle with no vertical component? You have a perfectly flat cone. No, there's always gonna be some little height of the cone. And you know why? Because well, there's always gonna be some vertical force involved because there's a weight. Can you guys make a free body diagram on that ball at that moment? It is in motion, right? So it's got some velocity maybe like out of the page, right? It's just swinging around. Okay. Draw the free body diagram for that ball at that moment. Trying to give you guys a head start here. Because if you guys need this before I reveal the answer, then give a chance to know how to do it. Oh, if you guys draw a weight on this ball about like this and call that mg, and a tension force that goes about like that, and label it something to do with tension. Now I'll label F sub T like tension force. Capital T is also okay, but I'm going to avoid capital T for this one because that could be very easily confused for like time period. Okay, did you guys draw that? Did you guys put any other forces on that ball? Or is that it? That's it. That's the whole thing, right? Unless you said like air drag or something, but we normally ignore that. That's it. That's the whole thing. Hey, is that ball in equilibrium? Or is there a net force on that ball? There's got to be a net force on the ball because it's on a curved path, right? So anything that's moving in a curved path, there must be a net force. Maybe something that's acting as a centripetal force. Let's do this. Let's break this tension force into components, either up and to the right, or actually I should do that. Last class I did to the right and up, but let me do this other way. Call F sub T this way, and then break this into components this way. I think this would be more apparent what's going on. Right. Notice I dashed those vectors. So try to avoid drawing them at all on the actual AP exam, but you really have to draw them, make sure you dash them. Otherwise you're double counting the vectors. Okay. Oh, do you guys see that this component exactly balances the weight? Look at that, right? You guys see that? Right? In fact, if you had some numbers associated with this, like the mass of the ball and the maybe like the angle of pitch, do you think you could start to do some trigonometry analysis and maybe set this equal to this or something? Okay. So, okay, so that just tells you that there's no vertical net force on the ball. Okay. But look at the side bit right here. What could that be equal to? Well, I need some angles. Let's say I call this angle alpha. Is this angle right here also alpha? Is this angle here also alpha? No, it's something else. Okay, I'll call it beta. What is alpha plus beta equal to? 90 degrees. Yeah. So for example, if alpha was like 30 degrees, you would know beta is 60 degrees. Okay. So when you get this component, this could either be tension force times sine of beta, or it could be tension force times cosine of alpha. Or you know what this could be? It could be the weight, because this right here is equivalent to the weight, multiplied by tangent of beta. Right? Ooh, actually, I like that one. I'm gonna write that one down. Weight times tangent of beta. That's one way you could get that. Right? And this component represents what kind of force again? Centripetal. So couldn't you also say that this is equal to mv squared over r if you had to do something like that? Right? Maybe giving away too much stuff. I'm just trying to do like a big thought process for this. Obviously, these aren't all being asked on that quiz, but maybe something in this, right? How about this? If you guys did a lab back in October that involved a PVC pipe and a couple of Play-Doh canisters, guys remember that? It actually looked a lot like this, didn't it? Okay. And we assumed away the weight and just went with tension force. We said this is approximately a horizontal circle, which it pretty well was. I mean, it was a very, very flat cone. Okay. So would the tension force be, well, I bet you can figure out based on what's up here, right? But then if you said, well, it's not really, the tension force isn't exactly the horizontal component, right? There's also this vertical component too. Couldn't you combine these using maybe like the Pythagorean theorem? So like if you go back and include the weight and the horizontal part that's actually keeping it in a circle, you combine effects and the Pythagorean theorem and get that. Okay. Now that's what I want you guys to see, why there are like two answers per option. Okay. And I do want you guys to be able to, once you figure out one, get the other and see what that relationship is and the fact that they aren't really that different from each other. Okay. Guys go there? Okay. Ooh, a car going around a banked turn. Okay, so you guys see this car on this bank, and it's maybe we're looking at the taillights of this car, and this car is going into the page, right? It's going into the page and like around. Maybe it's like making a left turn. Okay? And the question is, what force acts as the centripetal force that pushes the car into a curved path? So I'll give you guys a huge hint here by helping you set up a free body diagram for that situation, because it's different than the block sliding down the incline. Okay. Oh, maybe I'll do it side by side. That's what I should do. Okay. So two different scenarios. So block sliding. No, yeah. Okay. Let's say down incline versus a car on banked road, say like turning left going into the page, something like that. Okay. Now at a glance, these might look pretty similar situations. Okay. Here's a block on an incline, some angle theta. Here's a car on a banked path. Maybe it's the same angle theta, okay, but this one's actually going into the page and it's going around this curve, something like that. Okay, so these you want to approach differently. Now the block sliding down the incline, don't you want to introduce coordinate system parallel perpendicular to the surface? This is not, what I'm about to draw here is not the answer to your guys' number one, but it might help you frame it. Okay. This thing has a weight. This thing has a normal force. And this thing has a probably some kind of friction force going on. Like that. Right. Do you guys see how the normal force is less than the weight? Right? Normal force is equal to weight times cosine theta, isn't it? Right. But that's not actually true for the bank car. In fact, the bank car, I'm not even going to set up a coordinate system that runs parallel to the surface. Right. Here's what I'm going to do for the bank car. Its weight pulls straight down, mg. Right. Now, for the rest of this free body diagram, suppose you are on a banked curve. You're going around a curve. Do you guys feel it? Like you exit the interstate, you're going a little bit too fast. Like, oh, okay. Do you feel inside the car? Do you feel really heavy or really light? Go around a banked curve. Heavy. Do you feel really heavy? Huh. Okay, so there's probably some kind of force change going on. Why would there be an extra force for me? Wouldn't you actually feel maybe like an extra force from the seat cushions pushing up on you? Right? Do you guys think that there's a normal force here that's huge compared to the weight? Normal force like that? Okay. Compare the situation on the left, situation on the right. Right. Situation on the left, the normal force was less than the weight. It's like weight times cosine theta. Situation on the right, the normal force is more than the weight. Huh. Why you feel heavy going, right? What if I break this into components, this normal force? There's no other forces, by the way. That's all the forces, just those two. So like, hey, would this balance out this weight? Huh. Okay. Guess that? I give you guys any other hints? Probably getting too close to that question, but that's a really good head start right there. Okay. Okay, number 9, I'm going to leave to you guys. Number 10, let's take a look at this one for sure. Number 10, because there's a good chance you get a question kind of like this on the actual exam too. It says planet Z has same density as Earth, but a larger radial size. So maybe it's made out of the same like dirt material, but it's like physically larger. Okay. Where's the gravity field at the surface of that planet? Okay, so I scaled it up by some factor, and all the answer choices are some factor in terms of Earth gravity. Okay. So, and I gave you guys a hint here. A larger radial size means 2 things. It means you have a larger mass and also a larger distance from the center of the planet. And those are opposing effects, right? Larger mass should be like more weight, more gravity field. The larger distance from the center is like a lesser effect, inverse square law, right? So what's going to win, and how does this work out? Now, in that one, maybe I was too nice with that question because I said the same density material. I want to give you guys here in these hints a more general idea. So, do you guys remember what is gravity field in terms of the mass of the whole planet? I'll point out where you can get this on the AP equation base. It's a combination of 2 equations. You guys see universal gravity force, Gm over r squared. Okay. And right beneath it, free fall gravity is your weight divided by your mass. Okay, well, if you put 2 and 2 together, isn't it just universal gravity divided by the mass of the object at the surface? So that's going to be Gm over r squared. That would be true, right? Gm over r squared. So capital G is universal gravity constant. Capital M is the mass of the planet. R is the radial size of the planet. Okay. I should draw that out. So we got radial size of the planet, mass of the planet, and G is 6.67 times 10 to the minus 11 meters squared per kilogram squared. And then what's the gravity field at the surface of the planet? And so now we're hopping planets. We're saying, well, what if we blow up this planet bigger, smaller? Okay. And I also want to throw in a variable of density. So what if you made this out of like different density materials? Like what if you ran into like a gold planet? It's like, oh, this planet is solid gold. It's a giant gold nugget. So you feel really heavy on that one. So how are you going to tackle this? Well, maybe what I want to do is look at this M and this R. This mass of this planet is not independent of this radius, right? The larger radial size, the more mass. These two, there's actually a relationship between these two, isn't there? Between this mass and this radial size. Huh. And it might have something to do with volume. So isn't mass equal to density times volume. Right? You guys remember that? Okay. That's actually also on AP equations. It's tucked down here in the bottom left corner. Density is mass per volume. So can you cross multiply volume and say mass is equal to density times volume? Right? You guys remember that? Okay, so I did a little substitution right there. Go from here to here. Let me spell this out. So here's your density. Here's volume. Right? But okay, I had to do that step because now volume compared to radial size. Now the planet is approximately spherical. Do you guys happen to know volume of the sphere?
4/3 pi r cubed.
4/3 pi r cubed. That's it. Yeah. So G times rho. Rho is this crow look at P. That's actually Greek letter rho for density. Yeah. Times 4/3 pi r cubed. Okay. Tell you what though, even if you did not remember that exact equation for volume of a sphere, that's okay. If you forgot the 4/3 pi part, the important bit is the fact that volume is directly proportional to r cubed. Okay? Because remember, we're going with this type of question. We're trying to compare one gravity field to another gravity field, one planet to another planet. Okay? So the whole 4/3 pi is going to end up canceling out anyway. Okay? But this proportion matters. Okay? All right, I'm getting you guys really close. This is a really good head start on this type problem right here. Okay. Let's play around with let's do a density question. Now I said same density, so this doesn't directly apply to that question, but what if you double the density of the planet? What would happen to the gravity field, all else equal? Wouldn't the gravity field also double? Yeah, because there's a direct relationship between these two. Okay, so something like that. Right. But what about like radial size? Okay. I think you guys can get that from there. Next thing, I want to do some exercises with you guys. So let's do an exercise that we actually did a couple of days ago, but was not recorded because there was an internet outage. So, I hope everybody can do this right now. Can you guys derive orbital velocity, or well, we'll say orbital speed from scratch? Okay. Orbital speed. No, maybe you haven't memorized, but even if you do, if there's an FRP question, AP is going to expect you to do this as one of your steps. So I'm going to draw this scenario out while I'm giving you guys a head start. So maybe jot down some equations, get orbital speed. I bet some of you guys know how to do this. Maybe everybody. Be a good thing. Of course, if you're taking notes a couple of days ago, you probably just turn back a couple of pages and be like, oh, there's the answer. All right, you guys remember how to do this? All right, so this satellite in orbit around this planet. Now I'm going to put it in, well, if this is Earth, maybe I'll call this like low Earth orbit, so that its orbital distance from the center of the planet is not much bigger than the radius of the planet itself. In fact, I'm just going to assume that they're about the same number. Okay. And if that's true, then one more thing. What's the free body diagram on this satellite? What's the free body diagram look like? How many forces are acting on that satellite? One. Its own weight. It acts straight towards the center of the planet. So I'll call it like F sub G, okay, gravity force. Okay. Now that gravity force is, isn't that acting as a centripetal force? So as the planet moves perpendicular to that, like this V vector and this weight vector are perpendicular to each other. Okay. The centripetal force is provided by that gravity force. Isn't that true? Centripetal force. mv² on r. which AP doesn't exactly give you this equation, but sort of does, almost. AP gives you centripetal acceleration right here. Its centripetal acceleration is v squared over r. But if you combine that with Newton's second law of motion, whereas Newton's second law of motion, F equals ma, okay, just multiply that by mass, you get the centripetal force. Okay, okay, so that's equal to, hey, universal gravity, G m over r squared. Okay, so this gravity force is providing this centripetal force. Oh, the mass of the satellite cancels out. So if you take a bunch of supplies up to the International Space Station, do you have to speed up the space station to keep it in orbit? No, you don't have to change its speed at all because it cancels out. One of the r's cancels. And then if you solve for v orbital, this would be for a circular orbit, square root g m on r. Guys remember that? All right, how about this? Let's go to an O'Neill cylinder. So we're up in space. There's no real gravity around, but we've got this giant disk that's spinning at a constant rate. I'm going to give this, let me do this. Let me give this, let's say 2 different tiers. I'll call this tier, let's say some radius r, and out to here, maybe like 3r. So I've got r and 3r. Guys got? But let's say it's all one solid disk. So maybe like there's this ladder that runs across the diameter, right? And there's people walking around here, here, right? Out here, all these people walking around. Now the people on the outside ring at 3r, they experience some artificial gravity. They close their eyes, might be really hard to distinguish that from real gravity. And the people on the inside ring, well, they feel some artificial gravity too. But is it the same amount of gravity? It is not. Who feels heavier? The guy on the outside or the guy on the inside? Yeah, the outside feels heavier. Okay. Now, you guys see this 3-to-1 ratio of radial size? I bet you could figure out exactly how much heavier, like proportionally. Okay. Does anybody know the answer to this? Right. How much heavier does this guy feel compared to if he walks up this ladder, goes to the inside ring? 3 times the radial size. Well, so this has to do with like a solid turntable disk. Okay. Give you guys a visual here. Okay. So probably something pretty close to what you guys are seeing right here, right? Something like this. Okay. It's one solid O'Neill cylinder. So it's one solid disk. Everybody everywhere has the same, what, linear velocity or angular velocity? Angular velocity. Remember Greek letter omega? Okay. So linear velocity, the guy on the inside is hardly moving at all. Compared to, let's say, somebody outside is like trying to radar gun at each of these people. Okay. The outside guys move a really fast linear velocity, but they do all have the same omega, the same angular velocity. They all make the same turns per time. Okay. So now that you guys have that visual, I'm thinking back to centripetal force. And we just applied this, didn't we, for centripetal force? Okay. mv squared over r. But you know what? That's actually not the most useful form of centripetal force for solid disks that are spinning. Notice I labeled this omega. It's the same omega everywhere, right? I'd really like to have an omega instead of a v, because the v is like different for everybody, but they all have the same omega, so I can compare them faster. Hey, isn't v equal to omega divided by r? Isn't that true? Okay. So I can rewrite this as m times omega on r quantity squared, all divided by r. Okay. So no.
Omega times r.
Thank you. Good catch. Good catch. You guys caught that right before I did. Yeah. Okay. So it's like, who's gonna pass this exam? Omega times r. Yeah. Oops. So let's scratch that. Okay, omega times r. Anyway, if you do omega times r, quantity squared, then divide by r, isn't that centripetal force equals m times omega squared times r? Right? Right. Okay. You guys get that? Now, what's kind of interesting is the old form of it. This is useful for like satellites going around planets, obviously. This could be useful for like a ball on a string, mv squared over r. Okay. That the centrifugal force was had an inverse relationship with the distance r. But in this other form, like a solid disk, where we just rewrote it, but is it kind of interesting that the centrifugal force is directly proportional to r? The other way it was inverse relationship. This one's a direct proportion. That's kind of interesting. Okay, and now we're really close to get to the answer. So if you, let's say you start in this inside ring, okay, and then you back up to the outside ring, okay, which is 3 times the distance. So if you triple this r, what happens to the gravity force on you? 3 times, right? Well, sorry, it's not technically gravity force. What type of force is it that technically holds you in a circle that acts as a centrifugal force? Maybe a normal force from the wall? Right? Just in case you get that type of question. Yeah, but it would be 3 times because this would be directly proportional to r for a rotating disk. Okay. Guys get that? Right. Let's do a modified outwood. Let's put a block up here. I'll call this guy like 9 kilograms. Connect it over a string over a frictionless pulley to, let's say, 1 kilogram. Can you guys solve for the acceleration of either the downward acceleration of the small block or the rightward acceleration of the big block? Oh, and let's say there's no friction. So I'll say coefficient of friction is equal to 0. Can you guys solve for that acceleration? Give you guys a head start here. So hope you guys are pretty close. You guys do acceleration as net force on total mass. Right? So that's Newton's second law of motion. Even if it was a double elevator outlet, you could still start with that. Okay. Then what is the net force on this 2-block system? Isn't it just the weight of the hanging one? Yeah, which is how many newtons? Yeah, 10 newtons. So here's a partial free body diagram. I do see 10 newtons of weight there. Okay. Now there are some other forces, but they are either internal, like the tension, or they cancel out, like the weight of the big block and the normal force of the big block. So yeah, so this weight is the net force on that 2-block system, right? And that acts on how many total kilograms? 10. Yeah, also I should change the numbers, but that would be 10, right? Because 9 plus 1, 9 plus 1. Okay. So what's the acceleration? 1 meter per second squared. Okay. You could also call out 1 Newton per kilogram. Sometimes the AP likes to do that, like newtons per kilogram. Same thing as meters per second squared. What is what's the minimum that any set like this could accelerate? Could be 0, right? Either you have a tiny mass here, or if there's any kind of friction that can stop it. What's the maximum any setup like this could accelerate? Yeah, pure free fall. Like what if there's a big old block here and there's like a little tiny paper clip attached to the other end of the string? That would be almost free fall, wouldn't it? It's not that. How about this? Let's follow the rest of this free body diagram. So I see there's a big old weight on this guy and a big old normal force that just balances that out. So this guy and this guy balance out anyway. So there's no friction. So if there was, I would draw a leftward force, but none of that. I do see an internal force that's probably pretty big, but less than 10 newtons, right? Probably pretty big, but less than 10 newtons. So some kind of internal tension force, F sub T. Okay. Hey, could you guys solve for the tension force? Now, how do I know it has to be pretty big but less than 10 newtons? Because there has to be a small net force on the hanging one so that it accelerates at a very small rate. Okay. That's what I was going to say too. So the acceleration of any system like this is bounded between 0 and free fall. In this case, it's a lot closer to the 0 end of the mark because it's a very small mass that's hanging. Okay. Could you guys solve for the tension force? which of course is also equal to this tension force. Two ways to do it. You can either focus on this free body diagram and go back to Newton's second law of motion and just focus on this and solve for the force that way. Or you can focus on the block on the table, but same method though. You would set up Newton's second law of motion and say that this net force causes that block to accelerate this much. Okay, solve that way. Looks like it's gonna be a 9th of a Newton, I think. No, sorry, not 9 Newton. That's like
Yeah,
9. Yeah, good call. Yeah, check me there. Yeah. All right, you guys pretty good on all that. Let's call that a wrap on today's